Hello everyone and welcome to Teaching Mathematics. Today we're joined by Dylan behind the computer and Craig is our guest today. Hello Craig.
Hi.
Okay, before we get into the show, remember that you can talk to us using the hashtag VTMaths. So that's the letters VT and maths. I'm sure we all know how to spell maths, don't we, Craig?
I hope so.
Now Craig, before we go further, why don't you tell us a little bit about yourself?
I work currently in the WITS Maths Connect project at WITS University, which is a professional development project where we work with maths teachers.
Okay.
And yeah, we've been doing a lot of, I think, good work with teachers, particularly focusing on functions and algebra. So
Oh really? So it's more FET phase rather
all
than...
high school, so
Yes.
from grade 8 right through to grade 12.
You must have a lot of interesting things to tell us. I look forward to it.
Well, I'm looking forward to it.
Now, we would like to, before we go on to what the content actually is about and how to teach it, we'd like to look at a couple of mindset resources we have. So let's take a look. Okay, I have managed to find 3 links to 3 different lessons, all on trigonometric functions. Now, I remember when I taught this for the first time, I was completely overwhelmed. And so I did go and look at some resources on the internet. Of course, in those days, there weren't as many resources as there are now. And you'll see these resources displayed on your screen, 3 different YouTube clips. And Dylan has got one stored for us to look at very quickly. I think that's Natasha busy teaching us about trigonometric functions. So basically, if you are lost and you need a little bit of a brush up, why don't you take a look at these links and teach yourself? Now, let's get on to the content. We move on to what's happening in grade 10 trigonometry. Of course, Craig, I made a mistake there. It's not grade 10 trigonometry, is it?
Well, that's Trig.
Well,
It's
okay.
a part of Trig.
Now that we've opened that door, why don't you tell us what we should know before we start trig functions?
Well, I think what's important to realize is learners have done grade 10 Trig probably in March. So they were introduced to Trig for the first time. So they've learnt about the Trig ratios, sine, cos, tan, and then also sec, cosec, and theta. Although strangely enough, that's only required in grade 10 and not in 11 and 12.
Yes.
They've also looked at special angles, 0, 30, 45, 60 degrees, and 90 degrees. And they've done some work on trig equations, very basic work. And no doubt they would have done calculator work as well, of course,
Okay.
using their calculators.
And all of this is needed for trig functions.
Yes and no. Today we were not going to talk that much about special angles, for example, and we won't talk that much about trig equations. Whereas if it were grade 11, I think we would be talking a lot about trig equations and the connection to graphs. But then, of course, there's also all the functions work. So I don't know if you want me to talk about that now.
Yes, why not? Tell us
Because,
about
of course,
functions.
trig functions is about bringing trig and functions together. And so if I understand correctly, according to the work program, learners have been doing functions for the last 4 weeks.
Yes.
Of course, being 2014 and having all these interruptions,
Oh,
I'm
it's
not
been
sure
wonderful, hasn't it?
how well teachers are coping with covering all the content. But nevertheless, the design of the work program, I think, is really good from a trig functions point of view, in having trig, then functions, then trig functions. I mean, just as you say it, it makes
Yes.
so much sense. So in terms of functions, the work that's clearly critical that should have come through is concepts like domain and range, maxima and minima, connecting representations, the intercepts with the axes, all those kinds of elements that are key to functions obviously apply to trig functions. And of course, we also have transformations, vertical shift and vertical stretch, and we'll talk about those more just now
Okay.
as part of trig functions.
It does sound like you've done an introduction to the section, the kind of introduction that a teacher would give. Would you recommend that kind of introduction?
Yeah, for sure. I think it's important, particularly given how many days learners might not have had school in the last couple of weeks.
Yes.
I think it's important to connect back to what they know from trig, from term 1, and then what they've been learning with other functions. The algebraic functions function in the same way as the trig functions. Trig functions have some special things, all functions. Each function has something special, but the big ideas are still the same. And I think that's very important for us as teachers to appreciate and then to communicate with our learners.
I think that brings up a beautiful analogy, actually. You could talk about every student in the class being the same, but still having particular qualities that are... And that's a good way to bring it all together.
I think so, yeah.
Okay. Let's move on to the actual content that we're learning in this section.
The content of trig functions focuses particularly on three functions. So that's y equals sine x, y equals cos x, and y equals tan x. So those are the graphs of the three basic functions. Notice that sec, cosec, and cot are not there as functions. And in textbooks and in the way we teach it, we always tend to focus a lot on the graphs because I think those are the things that are so new and so different. We work on a domain from 0 to 360 degrees, which is different, of course, because previously the domain's been real numbers when we've been working with algebraic functions, and we'll talk about that some more later. Then there's some new terms that come in, the notion of amplitude and period, which are key elements, and we'll talk about that some more. And then we'll go to the transformations, vertical shift and vertical stretch, as I've mentioned, which are the same ideas as we've had before in functions. And so it brings back work from the previous few weeks. And then, of course, there's graph interpretation, which we all know as teachers is work that learners really struggle with.
Yes.
And often we struggle to fit it in because we're running out of time often. And we get to the end of our time and we haven't done enough on graph interpretation.
Yes.
So
yes, and when Robin was here and we were talking about functions, whether it was grade 10 show or grade 11, I forget, but we found we spoke more about the shifts rather than the interpretation. And in many ways, as teachers, they forget that students don't realize it can go both ways.
And because we go from equation to graph, learners, it seems the work we've been doing with our teachers in our project schools, we can see that learners can go from equation to graph. But going from graph back to equation, or even graph back to table, which in some cases sounds a bit of a weird thing to do, learners really struggle with that. And I think as teachers we need to appreciate that and not assume if you can go one way, you can automatically reverse it.
Yes. I'm struck by an image actually of a child walking into a door and then telling them to walk back out again, just to break that stress that's associated with the moving backwards. It's not moving backwards, but using the skills in reverse.
And doing, there's this idea of doing and undoing.
Yes.
And there's a lot of that goes on in functions as we work with them.
Okay, you said we were going to talk about the amplitude. Let's take a look at it.
Okay, so amplitude, as teachers, as we know, the amplitude relates to the distance of the graph above some kind of middle line. And when we look at the graphs themselves just now, we'll get to see some of the important things that we really need to consider, because often we can define it in a way that actually could break down later. So this idea of amplitude is really an important one, and it's always expressed as a positive number. And that, I think, is important to recognize. And then also important, it only applies to the graph of the function sine x and the function cos x. It does not apply to the function of tan. And we'll see as we look at it why that's obviously not applicable in tan.
I am a little confused with this concept, and I'm embarrassed to say it because I feel like as a maths teacher I should know this. But in some textbooks I've seen that the amplitude is described as the height away from the x-axis. Is this incorrect?
So it's partially correct.
Okay.
So if you've got a graph where... Can we draw on?
Yes,
we draw on? Yeah, I think
please.
maybe it's helpful to do that. So if I've got... I'm having trouble opening the cookie. If I've got a graph, and I'm not going to put too much detail on at all, but if that's my sine graph doing something like that, then, and this is my y-axis, and this over here is my vertical axis, then often, as you say, we would talk about the amplitude being the distance away from the axis. And that would be correct, because the distance over here would be the same as the distance over there. The problem comes when we transform it. So, for example, if we shift that entire graph upwards, and let's say for argument's sake we have something that's doing that, then the distance from the axis to the highest point is not the amplitude. The amplitude is related to this middle line, and it's a horizontal line. The amplitude over here, let's try another color, The amplitude is this distance from the middle line. It's the same as that black one.
Okay.
But when we talk about it only being from the horizontal axis, as soon as we move away from the axis, then it's not from the axis anymore.
Yes.
And if we do measure from the axis, then we're not measuring the amplitude. We're measuring the distance from the axis, which is not the same always as the amplitude.
That's quite interesting. I suspect I'm not alone in my misinterpretation of what amplitude is. I found to cope with my misinterpretation, I'd avoid assessing it so that I didn't teach the wrong content. It's difficult when you find conflicting things in textbooks.
Agreed. And I think sometimes the tension that textbook writers have is that they know they're writing for a grade 9 or a grade 10 audience, and they try to simplify the concept in a way that a grade 9 or 10 would understand. And sometimes in simplifying it, we introduce a potential misconception.
Yes.
And I think that's a challenge that all textbook writers face. And I think as teachers we do the same. So, it's about being very, very careful when we simplify as to whether we pushing a little bit too far and actually getting a special case, and the special case becomes a definition, which of course will break down.
Yes.
When we're not working with a special case anymore.
Yeah, it makes a lot of sense. Shall we move on to period?
Okay, period's quite hard to in fact, both of these are quite hard to explain without drawing graphs. So I'm going to refer to this graph I've drawn already. What we can see on the screen there is that period is about the number of degrees it takes to produce a single copy of the function. So there's no repetition going on, there's one copy. And of course the big idea with trig functions is that they do repeat themselves. And we'll see that now as we look at some other examples. But if I extend this particular picture further, because in fact this graph goes up and down forever. If I want to know the period, it's from, take this point over here, all the way through to that point over there, because as we can see, this portion over here starts to be a repeat of what I've already got. And so this over here would be 360 degrees. And we can have a look at that some more just now. And that's the period. It's the number of degrees to get one full repeat, but not go further. We don't say the period is 0 to 360. It's not like we talk about domain. It's simply a single number expressed in degrees in this case to tell us how many degrees we've needed. Now, not every graph needs 360. For example, tan is different.
Yes, as you said earlier, tan is a completely different animal.
Tan is, yeah.
I seem to be full of these ideas today. I'm not usually, but I've thought of this and how to explain this in a different way, and tell me if it's incorrect. But you could explain it as the size of clothing you wear. Whether you wear the size of clothing, no, it's not working. Okay, my thought over here was that I remember one time when I was teaching this, I tried to teach that when the graph next reaches that point, that will show us how far or how big the period is. But of course, it reaches that point over there again, so the explanation didn't work.
Although, I like what you're saying though, because if we take this point over here, if you want, this is going up the hill.
Yes.
If you think of it on this blue curve. When next is it going up the hill? That is this point over here. Whereas the point you're pointing to over here is coming down the hill. So it's the same y value, but it's not in the corresponding position.
Yes.
And what I like about what you're explaining is that you've taken a more general case than I took. So I started on the axis and went all the way along the curve back to the horizontal axis. You've taken a general point on the curve and said, when next do I come back to that point? And actually, I think that yours is better than mine. Appreciating
you've made
your
me
concern,
feel much better about the bad analogy.
Yours is a more general case of explanation, and I think it's very important for us as teachers to be using more general cases and not only always a very specific case. So, yeah, I wouldn't ditch your explanation.
Okay, thank you. I feel a bit better now. Okay, if you have provided us with some pictures of the sine, the cosine, and tan graphs, why don't we take a look quickly?
Okay, so if you have a look on the screen, the first graph there is a better version of what I started to draw on the whiteboard here. And we can see there a single repeat from 0 through to 360 degrees. Okay, now that's the domain, as I mentioned earlier in grade 10, the curriculum says we only need to work from 0 to 360 degrees. And for me, the problem with that is that we lose one of the most powerful things about trig functions, and that's the periodic nature, that it continues forever, as I tried to draw on the whiteboard. But so the graph below goes to, is it 900 degrees? And it shows 3 full repeats. Am I right? 3 full repeats? No, 2 and a bit more, 2 and maybe 3/4, which starts to show you that it's more than just an up and a down and a back up again. And I think that that's very important. So I would encourage teachers, even in grade 10, when we're not theoretically needing to go beyond 360 degrees, I would say at least show your learners how it repeats, say up to 900 or 1,000 degrees. Let them get a feel for it, because in grade 11, it's going to be critically important that they understand it goes on forever. And in fact, it goes on in the negative direction too.
Yes.
I haven't indicated that here, but that is the case, and they'll come across that in grade 11. And in fact, some grade 10 textbooks also show negative, I think probably from negative 360 through to 0. So that's very useful to be able to see the repeating nature. And I think on the next slide, we have the exact same idea for cos. So exact same thing, we don't need to spend much time on it. The first one shows a single repeat, which looks like a valley. So it looks completely different from sine. But when you see the repeat, that the lower graph, looks almost exactly the same as the sine graph, except it's shifted over. And of course, in grade 11, we will actually explore these horizontal shifts and see that you can shift the sine graph to be the cos graph if you want, and vice versa. And so I think exposing learners to that in grade 10 is useful.
Yes. Maybe not.
Not to assess it.
Yes,
definitely not to assess it, but to give them a feel for this goes on forever. I think that's, it's not hard, is it?
No, I don't think so. You just carry on drawing on your blackboard.
Exactly.
There's no technology needed. Okay, now the different animal, tan graph.
Yeah, it really is a different animal. Okay, so take a look at that graph at the top. It looks like it has these weird kind of kinky things, right? And those vertical dotted lines are asymptotes. Now, learners have come across asymptotes in algebraic functions when they worked with the hyperbola, and also when they worked with the exponential function.
It's quite an abstract concept.
It's really hard. It really is hard. And I think that we shouldn't assume that even though learners have come across it before, that they really do get it. I'm not even sure that there are many grade 12s out. In fact, I'm pretty sure there's many grade 12s out there that when you really push them on what an asymptote is, they would struggle to explain. So I think we need to go easy on grade 10s if they're struggling with it. But what I wanted to show where you've got more repeats is that you start to see that there's this, I don't even know how to describe it, it's kind of like vertical, then it goes slightly diagonal, and then it goes vertical again. That kind of shape is the shape of every piece of the trig function. And notice that it's not like saying there's 3 functions in the top graph. It's one function, then in that case we can see 3 pieces.
Yes.
But when you see a bigger domain, you begin to see that actually there's no like halves. Well, I guess the first one on the left you could argue is a half, but it carries on the negative side. But all of those are the same. And I think that's another reason in this case for showing a larger domain, to be able to get a real sense of what this graph looks like. And of course it does the same every time. It's broken. It has what we call a discontinuity at 0 degrees, at 90 degrees and at 270 degrees, and so it goes on. And what's interesting here is that you see this graph repeats itself every 180 degrees.
Yes.
Whereas the other 2 graphs repeat every 360, and so the period here is 180 degrees. And that'll be really important in grade 11 when you're finding the general solution.
Yes.
That you kind of deal with tan in a slightly different way as a result. So that's a heads up for grade 11 trig functions.
Okay. And you said earlier that the amplitude didn't apply to tan.
Well, thanks for reminding me. So, just look at the graph. What's the maximum distance from the horizontal axis if we go back to the original definition? Well, it goes on forever. So we can't talk about a maximum distance. And so it's just a meaningless thing. Even if we found a middle line, so if you imagine shifting that whole graph up so that like kinky part is, excuse the word, is above, is sitting, above the horizontal axis. Even still, you can't talk about a highest point or a lowest point a max or a min.
Yes.
And so therefore we don't talk about the amplitude of the tan function.
Are they ever asked that in assessments?
I would hope not.
Okay.
I mean, it's a real trick question.
It is.
And I kind of think, I mean, trig counts about 20%, I think, of
Trig
the
as a
overall grade.
whole.
And why waste a mark on that? I would think that's a bit of similarity with the rest of algebraic functions. Well, algebraic functions are in paper 1, all trig. Functions, triangles, all that stuff is in paper 2. And I think that's important for learners to know, that they don't pack away their function knowledge after they've written paper 1.
Yes.
They need to have it with them for both papers.
Yes. It's a common mistake, actually. You find it when you're marking your papers. Paper 2 suddenly, I don't know what Q does.
It's different too. It's not paper 1. Yeah.
Yes. Okay, and the next slide you've got shows us how to shift, I think, up and down.
Okay, so the vertical shift it should not be new to learners.
Yes.
Because they've done it with the functions that they've just been working with in the last couple of weeks. One of the things that I think the trig function, the sine and cos function really help us to see is the impact of shifting the function on the whole graph. So when you have a straight line or a parabola, you can't see the whole graph ever because they carry on infinitely, at least in one direction. Whereas if you have a look at that cos function, the black graph is what some people call the parent function. So that would be y equals x or y equals cos x or y equals cos theta. We've shifted the whole graph upwards. Now that means that every single point has moved up by the same amount. So in this case, you can see the intercept with the vertical axis was at 1 on the parent function, and on the orange graph, it's at 3, which means that that point moved up 3. All the other maximum point moved up 2. Thanks for correcting. All the other maxima also moved up 2. All the minima moved up 2. The points that were on the horizontal axis moved up 2. Every single point has moved up the same amount. And I think that's something that learners often don't get. They think that graphs are kind of this magic squiggle thing that somehow you draw. And one of the things we've been emphasizing recently in our work with teachers is to emphasize with learners that graphs come from points. And points come from the relationship between the input and the output. So if you change the input, if you change the relationship between them, so in this case if we add 2, then the output is going to be 2 bigger. And every point is now 2 bigger in terms of its y coordinate, and so therefore it's moved up 2, or moved down 2, or whatever the case might be. I mean, we don't have lots of examples, but that one was one I hoped would show how easily we can show that the whole thing has moved up, because we can see the entire graph in a vertical space. Obviously, we can't see it in a horizontal space. And I think a similar thing happens with the stretch, that I think trig graphs are really powerful in helping us to make sense of what a stretch does to a graph.
Now, the shift would be quite easy to show in a classroom with the standard overhead projector and the transparency.
Absolutely. Absolutely. And I've done that often. And I think when you've got one film of transparency with your graphs on, and then a separate film, a piece of transparency with the graph, and that you can then slide around up or down, left or right even, you can flip it over to show the reflections. I think we've kind of forgotten about the overhead projector.
Yes.
It's kind of modern technology means
tool.
The overhead projector doesn't need to be there anymore, or doesn't get used anymore, and I think that's a pity.
Yes.
I think it's a real pity.
Okay, the vertical stretch. Now that's when you multiply the ratio by a, I assume.
By some constant, and in the textbooks and in the curriculum documents, it's kind of ax squared, a sine x, a
tan?
b to the x, a tan x. I'm trying to think of the other functions that learners have come across recently. And I think what this really shows is that some points don't move. And those are the points on the axis, on the horizontal axis. It's kind of like the graph is pinned in there. So if you imagine somehow that you've got this wavy elastic band that's pinned onto the horizontal axis, if you pull the loose bits, then the maxima are going to go out even further because we're multiplying. In this case, we're multiplying by 3. Am I correct? Yeah.
Yes.
So we're multiplying the positives by 3, so they go. The 1 goes up to 3. And we're multiplying the negatives by 3, so the negative 1 goes down to negative 3 degrees. Well, when you multiply it by anything, it's still 0. And that's why it hasn't moved. And hence, thinking about it as a pin that doesn't let this point move, I think is helpful to imagine this elastic band. When you pull it, it can't move because the pin is keeping it in place.
Yes, I think that's a good
Yeah.
way to think about it.
And sorry, just to repeat that, and I also think it helps to show this when you've got more than one repeat,
Yes.
not just to show it for a single repeat. What you do in test and exam, whether you show them multiple, I don't know. I'm afraid I'll leave that to teachers to make the decision. But I think if you've taught multiple repeats, to show it in a test might be the fair thing to do.
Yes, that's
To
true.
show only a single repeat might be unfair.
Mm.
I'm not sure, but it's a thought.
It is a thought.
If assessment's about teaching assessing what we've taught, then we need to be consistent.
There are some that say that the assessment should extend their knowledge and you should apply it in new situations.
Well, that's one kind of assessment, and I think that's right, but I think that's only a very small. We want to know that learners have learned what we've taught them.
Yes.
And I think that's where we need to start.
And I hate these assessments that are all surprises.
No,
One
I
or
think
two surprises,
that's not
yes,
I
but
really do think that's
no.
not fair. Then it means, why did I study if I can't recognize anything that's here?
Okay, you've got two slides on these shifts and transformations, or let's just call them transformations because that's what they are.
Together, yeah.
And they basically say what the Q does and what the A does. Now, when we were talking about this earlier before the show, you brought up the fact that this should strengthen the knowledge that they have already in functions. And I think we should talk a bit more about that rather than going into
Looking at the
detail.
points, right.
Yes.
So, I mean, I've highlighted in red there what's the same. Plus Q is what learners probably see in many textbooks. X squared plus Q. X plus C. It's the same idea. Right.
Yes.
So it's about the vertical shift because you're taking the parent function, in this case sin x, and you're adding a constant onto it, which means the y value gets bigger by the same amount. And I think that it's very important for learners to see that this is the same thing they've been doing, but it's just a different kind of function.
Would it make sense then to draw a parabola and then show a shift up or down, and then draw the sine graph and show the same shift up or down by the same constant?
I think so. Yeah. Of course, you couldn't do them on the same set of axes
No.
because
That's
the
very
trig ones
true.
have degrees on the horizontal axis, but the principle is still the same. And so I would agree with actually going back to what we did a few weeks ago with the parabola. I think would be something important to do.
And like you said, it will strengthen that knowledge. It
It
will,
should.
that revision of parabolas, especially
It
with
should.
all these holidays.
For
Yes.
Sure, for sure. I think the same is true of the vertical stretch, and that's why I've highlighted that in red. So previously we would have seen things like ax squared, a times b to the power of x for the exponential, for example, or a over x for the
Yes.
hyperbola. And all those things are repeating. That's the thing that stayed the same. The thing that's changed is the actual function, the individual function that we're dealing with. So while we're saying we're stretching them, we're shifting them up and down, those are all the same ideas. It's the same ways of operating with the functions. But we're choosing different functions now to operate on, and we see different things as we do that. And as I've tried to argue, I think the trig functions help us to see some of these things more clearly
Yes.
than possibly we see with a parabola, for example. I mean, one of the things that I think we all are challenged by with the parabola is that when we multiply by a, we talk about it getting, and I know Robin talked about this, getting further away from the vertical axis and
Yes.
getting closer to the vertical axis. And that looks like it behaves differently to the sine function. So the sine function, you can very clearly see this vertical pulling in both directions. But with the parabola, it looks like it's moving in and out. Now, we've got to be able to explain that actually the stretch is the same thing. And I think that's a really difficult issue for teachers. And unfortunately, we don't have time to talk about it today, I don't think. But it is something that I know I talked about. It gets flatter and thinner.
Yes.
But if the stretch for the sine function and the cos function pull it vertically, then how come for the parabola it's going left and right? And in fact, for the straight line, when you make a bigger, it almost looks like it's rotating.
Yes.
If you imagine an mx and the value of m getting big, it kind of looks like it's rotating towards the axis, which is another thing that looks weird if this is supposed to be a vertical stretch.
Yes.
So that's something for another day, I think,
Yes.
to talk about.
I hadn't actually ever thought of A as a stretch. I thought of it more as a change in shape.
And you see, I think that's the key thing. The curriculum documents talk about it as a stretch, and I think textbooks talk about it as a stretch. But what learners actually see visually might not appear to be a vertical stretch. And I think it's really important as teachers that we're aware of that.
Yes.
Then we need to think about how we deal with it. So, yeah.
Okay.
I mean, perhaps one thing just to mention is the issue about the reflection. We don't have examples here which talk about the reflection. But the reflection operates in the same way. So when A is negative, it's a reflection in the x-axis.
And they will know that, especially from the parabola and from the hyperbola. The exponential as well.
And from all of them. It's sometimes a bit harder to see when you're so used to seeing the trig function. And sometimes with the trig stuff, when it's flipped on the axis, it's kind of like a bit harder to see.
Yes.
And so I think we should appreciate that learners might struggle with that in the beginning. But it's a function. We've done the same things. It's going to behave in the same way.
Yes. Okay, the transformation of tan, pretty much the same note, only you've said there indicate how 45 degrees and 1 has moved under vertical stretch and under
and in both cases. I mean, one of the things with tan, given its shape, is that when you stretch it, you can't really see much difference.
No,
right?
you can't.
So in order to say, well, this has been multiplied by 2, so I've now got 2 tan x, for example. I've taken the point, or the input value of 45 degrees. I've taken tan of 45, which is 1, and then I've multiplied it by 2. So instead of having the point 45, 1, I now have the point 45 degrees 2.
Yes.
And to show that point helps to show that there's, as a learner and as a learner, that I recognize that it's moved. And I think for us as teachers to be showing learners, see, this point has moved. It's not just, this is a badly drawn version of what we had before. And of course, the vertical shift you can show slightly, because that kinky bit, for want of a better word, is slightly above or below the axis. But even still, it's not so easy to indicate it. So by emphasizing the point 45, 1, it forces us to pay some attention to where that's moved, depending on the transformation that we've performed.
Okay, now we are going to talk about how to do this practically. So let's get our notes out and let's get practical. Okay, well, let's get practical. How do we teach this? We've only got a week, apparently, to teach all of trigonometric functions.
You're right. When I thought about it's only a week, it seems really short, but actually I don't think that it's impossible. When I think of some of the other sections where we have to teach stuff in a week, I actually think that maybe trig is not as tough as
especially with the build-up we've had, with the trig
and the functions. Yes, and we have to capitalize on it. So one of the things that I've seen many textbooks do, and I've done it myself, and I'm pretty sure that many teachers can identify with this, is that we give learners a table of values with special angles. So we've got, imagine the top row, 0 degrees, 30 degrees, 45, 60, 90, and we keep going to 360 or more. And we say, complete the table.
Yes.
And then we want them to plot the graph. And I'm sure you can remember that you end up with graphs that don't quite look like what you expected.
No, they look nothing like
they look, and I kind of think if we've only got 5 a week to do this, then really we need to be careful about capitalizing on the time. And so I'm kind of done with this thing of giving the table, getting learners to fill it in, because I think they're not sure what they're doing. They're not sure of the purpose of completing the table. So one of the thoughts that I've had, and can we try it on here?
Yes.
So.
Okay, so basically we can't see a very clear picture, so I'm going to describe what's here. We've got the vertical axis, and it starts, there's 0, and it goes up to 1, and it goes down to -1 at the bottom. And then every grid line is 30 degrees until we get to 540 degrees over there. Okay. So what would you do with this?
Okay, well, one of the thoughts I've had is that we want learners to participate with us in trying to get the shape of the sine function. So now I'm going to assume that my learners have got calculators and they know how to say sine 30 or sine 45 or whatever the case
Well,
might
let's
be.
hope after the trig.
And that they can get the answer and they can call it out to me.
Mm-hmm.
And I'm then going to plot it. So I'm not asking them to do stuff in the books. I'm asking them to follow with me on the board, and we're going to build this together. So a typical example, we might say, what's the value of sine 30 degrees? And hopefully they will on the calculator, or they might recall from special angles that sine of 30 degrees is 0.5. So that's roughly there
Okay.
on our thing. And then I'd ask them for a whole bunch more. And then I'd ask them to choose. So maybe I'd say, what's sine of 90? And they tell me that it's 1. And then I'd ask them to choose some values. And no doubt they're going to get a range of values, and they're not going to come in order. And I'm not going to worry about that. I'm simply going to plot the points that they give me. And of course, I need to be roughly aware of whether their answers are correct or not.
Yes.
So that's something that I would need to bear in mind. But sine 60 degrees is 0.866. Is that right? So it's somewhere around there. Do you want to hit the calculator? So how about you just give me 1 or 2? If I tell you I want 100 degrees, what's sine of 100 degrees?
It is 0.98.
So that's really close to 1. So 100 degrees, trying to get vaguely accurate, is pretty close to 1.
Okay, I'm ready for the next one.
Give me anything to 0.4 on this scale, and I probably pushed it a bit too far. All right, so now what about sine of 300 degrees?
Sine of 300 degrees is negative 0.87.
Negative
Roughly.
0.87, so that's somewhere over here.
Yes.
Okay, so I would keep going with this and ask learners to give me values, and they can go up to 500 degrees if they want. They can go up to more, but obviously we're constrained here. And I'd plot these dots and say, okay, what's happening? And then I would...
Sounds like quite a quick process.
Well, I'm hoping that it would be, because I think you might have 30, 40, 50 learners in your class. Maybe there's 20 calculators between them, at least. And so lots of answers can be coming out quickly. And in effect, I don't think I'm even recording these on the board. I'm just plotting the points at this point. Because then I want to say to learners, well, does it ever get bigger than 1? Can you find a point where it gets bigger than 1? And hopefully some of them will take that up and be playing on the calculators and seeing. And of course, if they do get an answer bigger than 1, then we know that something's gone wrong, because we know what that's going to be. And of course, at some point, we're going to get, more or less, we'll get these points that will start to show us, okay, this is the shape. Then I'm thinking that might be the point to say, okay, now go back to your textbook and to that table that I've just said I don't like. And now work on the table, complete it, and then draw the graph. And the advantage of that table in the textbook is that it's systematically, you're moving from left to right and you're filling in as your degrees get bigger. Now, of course, this could be jumping all over the place. And so from that point of view, it's a little...
I don't know,
that's one
I quite
potential
like
problem.
that.
But I think it's about... I mean, I can imagine we've got some points that are above the horizontal axis and some that are below. So now the question will be, does it ever cut the axis? And if so, where? And so we might have some learners who kind of choosing values in that particular zone, if you want, and saying, oh, here it's positive, there it's negative. Can they ever get the 0? Now, of course, some of them might remember from their special angles.
We hope.
180 is not a special angle, so who knows? But you can say, okay, fiddle around, or maybe that's not a good mathematical word, but check on your calculator, investigate what's going on for angles just less than 90 and just larger than 90 degrees. Can we figure out what's going on there? Likewise, around 270.
Yes.
Is there another place where it gets to 1? It's those kind of questions that I think we can't... I mean, I can imagine learners kind of shouting out and going fairly crazy, but they're doing maths.
Yes.
And we're working on this thing together. What's really important then, I would think, is that learners should have... Maybe then they copy this down. Just rough sketch of what we had. And then maybe for homework, they go to their textbook and they do it systematically and they do it neatly. So I'm thinking that this would be more productive than getting them to just blindly fill in the table and try to draw the graph. And of course, sometimes the graph is sitting on the wall because we've got a poster that gives it, right?
Yes.
So we also need to be aware that sometimes the answer's already there. They might just not be looking at it.
What I like about this method is it gets them used to coordinates almost immediately, or the coordinates on the trig functions. You're talking about 30 degrees. You're not talking about 1, 2, 3, 4. And
Absolutely.
where is it along
and I
the
think,
vertical?
you know, we often, some of the stuff that we hear, we've heard a lot of in the last 10, 15 years, is that we want learners involved, and often that's interpreted as learners at the board doing the work. And sometimes it's not productive to do that because it slows things down.
Very much so.
And we lose time. So
Yes.
I would not suggest that you have a learner at the board plotting the points, because you don't want the plotting of points to be the major feature here. You want to talk about where the point is. So you want to I would do that as a teacher. I'd plot it, hopefully I'd get them right, and then we can talk about them. Not have this whole discussion about did the learner actually plot it in the right place on the board. You know, it might be a good idea. I mean, I would think it would be important to have a big grid on the board. And so teachers would need to figure out,
overhead
depending
projector.
on or an overhead projector. I mean, if you have a data projector or an overhead projector, one of the things I've done, which I think is I project it straight onto the chalkboard, not onto the screen, because often the screen is too far away or too small, but project it directly onto the board, and then, you know, it's easy to erase and start again.
Yes, and especially now. I stopped that sentence. Now, could you teach shifts at the same time, or would you recommend that we do all the parent functions like this, plotting points and then talking about the shape, and then once we've had a day to mull over it, then do a shift?
I think that I would do sine and cos together. Okay, and I don't think so. I know so. I would do sine and cos in a sense together. So I would do this for sine and I do it for cos in the same way. Although maybe learners could then do the cos one on their own at home if they've got this idea. But I would keep sine and cos parent functions together. Then I would do the shifts and stretches. And then I would go to tan. Because I think tan operates so differently that by doing sine and cos together, I think we reinforce similar things.
Yes.
And keeping tan aside,
it makes a lot of sense.
Yeah. I just think that because it behaves so differently, I would keep the stuff that's similar together in the beginning. Tan behaves differently because of the nature of the function, but the ideas are still the same. Plotting the points. I mean, you could have a great fun with tan, really. Because when you ask learners for tan of 90 and the calculator says error or whatever it says, you can't say, check, did everybody get that? Maybe your batteries are flat. Or, tease them. Your calculator's not working. And then start to explore, well, what goes on just before 90? What happens with tan 89? Tan 91? What about tan 89.5? And push them into this idea. And maybe they will come up themselves and say, this seems like an asymptote kind of thing, like we had with the hyperbola.
Sure, you
Possible?
could award extra points for an answer like that. But it might actually be worth exploring, to put the challenge out. Why does it not exist at 90? See if they can come up with a solution.
And we can see, and we'll talk about that a bit more just now. So I think this plotting points with the class together is something that might be worth pursuing, rather than complete the table in the textbook. And I think one of the key things is that the learners start to take ownership of this, and they can say, I want to focus on a particular thing and do something. And they might do 10 calculations, or with 10 calculated presses, what do you call them, in 10 seconds. Whereas if you ask them to fill in the table, they can take 15 minutes.
Yes.
Because it just doesn't, what's the point of doing it?
There's no competition, there's no...
So I think there's something there about the energy that we could capitalize on. And teenagers have energy. We've got to just direct it.
Yes.
There's no question that they have.
They've got fantastic energy. Yeah. Now, after we plotted these, what would you do next?
In terms of the sine and cos?
Yes.
Then I would start to look at... Then I would want the learners to be able to see focus on the periodicity. So focus on, do we see that it's repeating? And then start to say, okay, with the previous functions, we stretched them and we shifted them. Let's do the same thing here.
Okay.
And I guess you could say, what do you think is going to happen? If we shift this graph up, what's it going to look like? I don't think it's that difficult to imagine for learners what it's going to look like. And then, why does it do that? And then we can.
Would we go into why it has the shape it does? For example, the unit circle.
I certainly would do that. So the unit circle is something that I think many grade 11 teachers work with. And I think it comes out, it's used in the grade 11 textbooks. It is used in some grade 10 textbooks, but I think that it would be something for grade 10 teachers to consider looking at, because I think it helps to start explaining why this graph looks the way it does.
Okay. Now, you did find some links for us to look at with the unit circle. They're from on screen at the moment.
The one on, it might not look particularly fancy, but don't underestimate the skill of the person who produced this. Okay, so there's heaps of stuff out there. So this is from GeoGebra Tube, and what it does is show us a circle on the left with some colored stuff, and and then there's things on the right with blue and red. I want us just to focus on the left first. That thing is what we call, that circle is what we'd call the unit circle. And it's called unit circle simply because it has a radius of 1.
And sometimes it's used when we talk about special angles.
Correct. Sometimes we use it is, and so teachers and learners might have come across it. Sometimes with special angles, I think they work with the radius of 2.
Yes.
Because it helps to simplify some of those horrible.
It's one of those textbook dependent things.
So we have a radius that's rotating around the circle. So Dylan, if you can just drag the slider, you see that thing rotating. So just drag it. Forget about what's going on the right for now. Just have a look at that thing that black line that's rotating around the circle. And there's an angle there that's growing in green. And that's related to where the mouse is. It's simply sliding to make the angle bigger.
Yes.
Okay? And so we're going around the circle. And that's what I like to call a rotating radius. And so we can go clockwise or anti-clockwise. And as we kind of undo it, it wipes out some of the stuff. Now, I'm sure people were not listening to what I was saying. They were looking to what was on the screen. And so they would have seen a sine graph out there. Now, what's interesting about that is the red line that's in the circle is connected to the red line on the right-hand side. Okay? And so as we move, what that thing's called a slider. So as we rotate around the circle, look what happens. We get this thing that has the shape of the sine curve. So it goes up to +1, it comes down, and you'll see that'll be 180, and it'll leave a 180 on the horizontal axis. It keeps going down, and then it gets to a minimum of -1 at 270 degrees, and then comes back up again to 0 at 360 degrees, which is slightly off the screen. Okay. Now, and sometimes I wish whoever developed this had let us go around the circle more, because as we go beyond 360, we just get that wavy pattern continuing to the right. But nevertheless, this is I like this because it's so clean and neat, and it doesn't have lots of other stuff on it. Now, there's heaps of things that we can talk about here, but let's just take the example of at 90 degrees, why is the graph at 1? So when the angle is 90 degrees, we get to a maximum, and that maximum is 1. And now, why is it 1? And the way I would talk about it is to say to learners, let's go back and think about the definition of sine theta.
Yes.
Sine of theta is y over r. In this case, r is 1. Okay? But it's actually not that important, because when we get to 90 degrees, the y coordinate of the end of that line that I'm rotating, that's radius that I'm rotating, because it's sitting on the y-axis, the y value of the end of that line is the same as the radius. Okay? So y divided by r is
1.
Something over itself. So
yes.
It's 1 over 1, which is 1. And that's why at 90 degrees we get 1. We can do all the others. If we think about sine of 30 degrees, sine of 30 degrees we should know is a half from special angles. And so when we look at y, in that case, is it a half? I hope it is.
Yes.
And the radius, the r, is 1. So we've got a half divided by 1, which is a half. If we choose any other angle, we get the same kind of thing happening. And so we can explain why sine of 180 degrees is 0 if we rotate all the way to 180 degrees. Because the radius is now lying on the horizontal axis. So the y value at the end of that radius is 0. So we've got a y of 0 divided by an r of 1. So we've got 0 over 1, which is 0. And that helps us to explain why the graph has as a value of 0 when the angle is 180 degrees.
Yes.
So, I mean, we could talk about this a whole lot more and we don't have time. But that's the kind of thing that I think helps us to go back to the earlier work we did in Trig in the first term and use it to explain why the graph looks the way it does. And there are other apps there to do the cos function and to do the tan function, but I'm not sure whether we've got time.
Unfortunately, we are running dangerously short of time. So we need to skip through the tan function, but I will put the links up on the blog and people can go and click through them and use them. Thank you for finding them for us.
There are many out there, but These are ones that work in degrees. Some of them work in radians, which
it's very difficult to find in degrees.
Much harder, but nevertheless, hopefully these are useful.
Yes. Okay, shall we move on to good ideas? Yes.
Okay.
So good ideas, basically a section where we talk about a couple of points that experienced teachers will have learned by now to do, but maybe inexperienced. And
well, I think in many ways we've talked about several of these before. So I've already talked about what I think is the importance of emphasizing the repeating shape of the graph. And so that's about extending the domain. So I would treat that, said that's one important thing to do at grade 10.
Of course, if you don't emphasize the repeating shape and you only show 0 to 360, when they get to grade 11 and suddenly they're shown more, it's a big surprise, isn't it?
Well, and I would kind of say, why didn't the grade 10 teacher know this? You know, I mean, it's a bit rude maybe, but if I were the learner, I kind of think it's there, and it's one of the most important features of trig functions. We need to show it, even if we don't major on it. So the second one is to strengthen, as I said, strengthen those three key aspects: range, vertical stretch, and vertical shift. Because as I've already spoken, we can see it much more clearly with the trig functions. And so I would think that it is an opportunity to reinforce what's come before in terms of function, and then maybe to, in revision stuff, to go back to the algebraic functions and then okay.
So it's a constant revision,
it's
constant
backwards and
tying
forwards.
in.
These things are all the same. They're behaving in the same way.
It almost lifts the pressure. You're not learning something that's new. You're just adding to the knowledge you already have. And it does lift pressure.
And it's almost like saying, okay, if my learners didn't really get the idea of range yet,
yes,
while I'm doing algebraic functions, then when I come to trig functions, I really am hoping that they will get it, because there's things there that they might be able to see more easily. If they haven't got range after trig functions, then I'd be worried. But I wouldn't be so worried until I've done it in trig functions. So I think, again, it does take pressure off potentially, and saying, this is where I really want to nail this particular aspect. So if they haven't completely got it until now, I'm not going to stress too much, which means I shouldn't assess it too heavily up to this point.
Yes, well, I don't know how much assessment has happened in the last 4 weeks,
Possibly. Yeah. Then the range versus amplitude, I guess, is really about a misconception that we've already talked about right in the big. That we can. Sorry, we actually didn't talk about this earlier, although I think I meant to.
No, we did. Where I said that the one textbook told me that
that
it
was a
was
definition
the distance.
of amplitude.
Oh,
so remember,
yes.
the range is about minimum y value to maximum y value.
Okay.
Which for and sometimes learners think that automatically. What am I saying here? So range. Let's say in 3 sine x, the range would go from -3 up to +3.
Yes.
The amplitude is not -3 to +3. The amplitude is straight 3. It's a single positive number. So they're connected, but they're not the same thing. And I think that's the point I'm trying to make, to emphasize that, because it seems that learners often think, well, it doesn't look any different.
Yes.
But range is about saying minimum point to maximum point. Range is, amplitude is a single number. It's the stretch.
And it's always positive.
And we always talk about it as positive. Yeah.
Okay. Well, shall we move on to the pressure points for this section then? And of course, pressure points are the 3 points that things can really fall apart if we don't get them right. So what have you chosen as our 3 pressure points?
Well, I've chosen what I think are big ideas. The first is that trig equations for some learners can seem to be divorced from the trig they did previously. And I think it's really important that they do see the connections. And it's important as teachers that we emphasize those connections. And so that's what I was referring to when we use the triangles to explain, or when we can use the ratios, to explain why the graph looks the way it does.
Yes. Now, trig equations, you're not talking about general solution at grade 10
Not
level.
in grade 10, absolutely not.
No.
Trig equations in grade 10 is really 0 to 90 degrees, so it's only working in the first quadrant.
Okay.
And so we haven't talked much about them.
Well, it would be a trig section,
today.
wouldn't it?
Sorry, that is a typo. I've said trig equations is trig without triangles. I should have said trig functions is trig without triangles.
Oh, okay.
Sorry, I'm just seeing that now.
Okay, so it should say trig
It should
functions.
say trig functions.
Is
Apologies
trig without triangles.
to our viewers. The second one is a big thing about trig, which I'm sure learners have struggled with since they encountered it. The inputs and the outputs are different kinds of things. In all the algebra they've done, if the input was a real number, the output tends to be, in most cases, a real number. Here, the input's an angle, and the output's a real number. That's weird. So you say sine of 30 degrees, so the input is 30 degrees, and what pops out? A half.
Yes.
And that's quite strange, and so I think we shouldn't underestimate how long it takes for learners to get used to that. And my experience then when you're working with trig equations is that learners say to you as a teacher, should the answer be a degree or a number?
Yes.
Which says to you they haven't really got this thing. And so I don't think we should be cross or frustrated with them. I think it shows the struggle that they're experiencing, and we should appreciate that it is a struggle and give them time. They only started learning this stuff in March. We just started May, you know. It's not much time at all to get used to something so radically different. The final one there is this. When we talk about trig functions, in our examples on the screen, we've got things like y equals sine x. And then we talk about sine of theta is y over r, and tan of theta is y over x. Now, the x in y over x is the x coordinate, whereas the x in the function is the angle. And so we can also replace that with theta. So we can say y equals tan theta.
Yes.
Okay? We can say tan of theta equals y over x. And the x value there, when we're talking about triangles, comes from the Cartesian plane. It's a length. It's not the angle. And so textbooks shift between them all the time, and we have as well on our slides. And I think it's important that teachers are aware of that. And I think we all slip between them.
Yes.
And so when we talk about f of x, because f of x notation is a really new thing in grade 10 functions, suddenly you say f of x equals sine x.
And they're thinking that x is
that x is not a distance, that x is an angle. So we could say f of theta equals sine theta, it would be the same thing. So it's just about making teachers aware and sensitive to that, which I think is
it's never occurred to me that would actually be an issue, that the x, as we use it as sine theta is equals to, okay, it's y over r, but cos theta is equals to x over r would be confused with y is equals to cos x. It makes sense now that you say it.
And so, you know, when we've got all these things going on at the same time, if learners are confused, I would be like, you know, it means they've been looking.
Yes.
If they're saying, I don't get that this x is, how come you got two x's? Are they the same? I'd be impressed with that question.
I would be too.
It shows that they're thinking. If they haven't asked the question, it's a sense of they don't know what they don't know yet.
Well, you see, now I'm a little embarrassed that I only realized it's a problem now.
But I think as teachers, we use the stuff so easily.
Yes.
We're so used to it. We don't even see it. It's only when you start to think, hang on, for someone who's coming to learn this for the first time, you know, are they going to make sense of it? And so I think it's about, I'm sure I was the same, you know, so.
Oh, thank you. Okay, let's move on to teaching strategy. Okay, so you have put up a 5-point teaching. I like 5 points. They're easy to remember. I think most of this you've talked through with us already. The first one saying revising definitions of trig ratios and key aspects of functions. Then the second one, introducing the graphs. And I see that you've got tan theta with sine and cosine of theta.
So I've put, that's a good point. I contradicted myself, right?
Yes.
I guess there's more than one option there. I mean, what I have deliberately done is put sine and cos next to each other.
Yes.
So we do that together. And I guess it's a teacher's choice. I mean, there's no hard and fast rules here. You know, if you want it, some textbooks introduce all the basic functions in the same chapter. And then in the next chapter, they then start doing the transformations. And so they've introduced sine, cos, and tan, for example, and then in the next chapter, they'll work with all the extra bits, if you want. And so that's a personal choice. And so I guess it's also about saying consolidate the stuff with sine and cos together and then go to tan, regardless of whether you do transformations first or not.
Yes.
I think that point I would stick with.
After we had our earlier conversation, to me it made more sense to complete sine and cos with all of the transformations and then move on to tan and treat it completely separately.
So should we change the slide?
Oh, well, we can't right now. We don't have enough time, but we can verbally discuss this. And then you talk about transformations of sine and cosine, or the graphs.
So that's the vertical stretch and shift, which we talked a lot about.
And then a separate point for the transformation of tan, and then something that we haven't talked about at all, which is graph interpretation.
And we said that right at the start, that it's one of the issues that doesn't get attention. I think that there's two options here. I mean, I've put graph interpretation at the end because really it's often treated as a consolidation and there's several graphs all together. But it might be useful for teachers to think about doing some graph interpretation of sine and cos when they're dealing with sine and cos together.
Yes.
And then after they've done tan, do some graph interpretation related to tan. And then at the end, combine sine, cos, and tan on the same set of axes. Of course, then it looks a bit like spaghetti all over the place. But learners need to get used to that. Because they will see those things in the exams. And so leaving graph interpretation to the end, I guess, is always risky. But I understand teachers wanting to leave it to the end because they want to get through the other stuff first. It's a completely natural response. But I think we always do it to the detriment of our learners.
You know what might be an idea is if you do run out of time, to go and use clips like the ones we have on the Mindset Network where they do a whole lot of graph interpretation and send the students home with a memory stick of the show, and they must watch it and they must do the questions themselves. It's not ideal. It would be better to have a teacher there. Yeah. Technology will never replace a teacher, but
absolutely.
Second best solution?
Many ways. There's many ways to do it. And in fact, doing one graph interpretation question regularly for the rest of the second term until we hit the mid-year exams might be something worth doing. And it doesn't matter whether it's parabola and straight line or sine and cos.
It's the same idea.
And I mean, if we say we're going to take 5 minutes in every math lesson from now until the beginning of June to do something like that, we're reinforcing all the same things.
They'll never forget how to interpret.
Of course, we could say the same about geometry riders.
Yes.
But it is something that I think is useful to be thinking about. How can I keep getting learners to work at this stuff and keep building it forward as we move forward? Because functions is such a critical aspect. If they can't do functions in grade 10, grade 11 is a nightmare, grade 12 is a nightmare, and university mathematics, for those who want to go there, is really impossible. Functions is too important not to get right.
Yes. Shall we go on to our last segment, which is one last thing? Okay, Craig, over the last few weeks I've been reading this book called Champion Teacher. Teach Like a Champion. There we go. I'm the champion. The book is Teach Like a Champion. And every week I'll discuss one actionable point that happens. Today the actionable point is format.